let's talk about one of the most fundamental and frankly weirdest rules in all of physics. It turns out that every single particle in the entire universe, and I mean everything, belongs to one of just two families. That's it. And figuring out why that is, well, that's the key to understanding why your world is solid. So let's start with a really simple question. Why can't you walk through a wall? I know, it sounds obvious. It's solid. But why is it solid? Really think about it. Why don't the atoms that make up your hand just, slide right between the atoms that make up the wall? The answer has nothing to do with size. It has everything to do with a bizarre rule of quantum identity. You see, the secret isn't hidden in how we describe just one particle. It's hidden in how we describe a whole crowd of them. The universe has these incredibly specific rules for how to talk about a group of identical particles, like a bunch of electrons. And those rules, they have consequences that we can see and touch, literally, every single day. Okay, this is where your brain might start to hurt a little bit. In our everyday world, if you have two identical golf balls, you can still tell them apart, right? You can put a tiny mark on one, call it A, and the other B. But in the quantum world, no way. Two electrons aren't just similar. They are fundamentally, totally, 100% indistinguishable. They have zero individual identity. They're perfect clones. So, to deal with this clone problem, physicists use a tool called the wave function. You'll often see it as the Greek letter psi. Just think of the wave function as the ultimate rulebook for any quantum system. It has every single piece of information you could ever know about the particles inside it, their position, their momentum, the whole shebang. This brings us to a really cool thought experiment that gets right to the heart of this. So let's say you've got a system with two of these identical, indistinguishable particles. Now, what happens if, while you're not looking, they secretly swap places? How does that affect their shared rulebook, the wave function? And that is the absolute key question right there. I mean, since the particles are truly identical, swapping them can't change anything you could actually measure. The odds of finding a particle somewhere have to stay exactly the same. But does the rulebook itself, the wave function, have to stay exactly the same? Now, don't get scared by the equation. It just tells a story. All it's saying is that when you swap two particles, the rulebook, that wave function psi, is only allowed to change by getting multiplied by a special number called a phase factor. And to make sure our real-world predictions don't change, that number has to have a magnitude of 1. The universe is incredibly strict about this rule. And here it is. This is the punchline. It turns out there are only two possible outcomes for this swap. Not 5, not 100, not infinite. Just 2. And that simple fact, it splits the entire kingdom of particles right down the middle. It creates this fundamental fork in the road of reality. So here are your only two choices. Option 1, the wave function is symmetric. You swap the particles, and nothing happens. Absolutely nothing. The rulebook is identical. Option 2, the wave function is anti-symmetric. When you swap the particles, the entire wave function flips its sign. It becomes the negative of whatever it was before. And get this, every single fundamental particle is born on one of these two teams. It either has a symmetric wave function or an anti-symmetric one. There are no exceptions, no particles that are kind of in between. This is a non-negotiable law of nature. So, of course, physicists had to give these two big families names. Particles with that symmetric wave function, we call those bosons. And the particles with the anti-symmetric one, those are fermions. So let's get to know these two families a little bit. And this isn't just some abstract math, This choice of family is tied to a real physical property that all particles have called spin. Now, spin is basically a quantum version of angular momentum. You can kind of think of it as a particle's built-in intrinsic rotation. Okay, so bosons, they have an integer spin, like 0, 1, or 2. These are the socialites of the universe. Their symmetric nature means they absolutely love to clump together in the exact same state. Then you have the fermions. They have half-integer spin, like 1/2. They're the ultimate individualists. Their anti-symmetric nature means they have let's say, a much more standoffish personality. And we're so close to answering our first question, because it's that antisocial, individualist nature of the fermions that is responsible for, well, pretty much the structure of everything you see. It's the reason matter takes up space. But why? Why does a wave function flipping its sign have such a huge real-world consequence? How does this little mathematical quirk actually stop you from walking through a wall? Well, turns out that that anti-symmetric rule isn't just some weird little fact. It is the direct mathematical origin of one of the most famous laws in all of chemistry and physics, the Pauli exclusion principle. And what the principle says is really simple, but its implications are just profound. It says two identical fermions, say two electrons in an atom, can never, ever, ever be in the exact same quantum state at the same time. They refuse to share a quantum address, period. Okay, let's just walk through the logic here step by step. 1. We know for a fact that fermions are antisymmetric. That's their rule. 2. Now just imagine for a second that two fermions were in the exact same state. If you swapped them, well, nothing would change, right? It'd be meaningless. 3. But wait a second. The rule for fermions says the wave function must flip its sign after a swap. So which is it? Is it unchanged or is it flipped? Well, there's only one way for a number to be both itself and its own negative, and that's if the number is 0. And a wave function of 0 means that state can't exist. It's totally forbidden by the laws of physics. And that's it. That's the whole secret. The electrons in your atoms are fermions. This principle is why they can't all just collapse into the lowest energy level around the nucleus. They're forced to stack up into distant shells, one by one. This stacking creates the entire periodic table. It creates all of chemistry, and it creates the solid, stable structure of matter that stops your hand from passing straight through that wall. So I'll leave you with this final thought. The fermions, the individualists, they build the structure. The bosons, the socialites, they carry the forces, like light. But what if everything was a boson? If there was no exclusion, no structure, what would the universe even be? It would just be a featureless collapsed soup. It's the stubborn, antisocial nature of the fermion that gives our universe its shape, its substance, and the fact that we're here at all.